I think we have the world's fastest, first only high-speed A-class surface stainless press.
Wow, that's pretty nifty. I've never really stamped stainless steel without a coating.
I don't think anyone has.
So, well, there may be, but not me.
Certainly not for like an A-surface quality part.
Well, there you go. Two things I would have never guessed.
But this is, once again, a one-of-a-type process, a one-of-a-kind machine, never before used, never before seen in industry. And there's a whole series of these that they had to do in order to make the CyberTruck and to make it in volume. We are live this morning looking at Sandy Munro's incredible new interview with Lars Moravy. Lars gave him a tour of the exterior body panel manufacturing line at Giga Austin, and there is so much incredible information that is packed into this video. This morning I have Nick Gibbs from Investing Against the Grain with me, and we are both mechanical engineering nerds, and so we're just going to get right into this.
So this is our stamping building. We have three 5-stage tandem presses, a few transfer presses. That's our first of the 2 hot stamping presses. We also have our stainless steel straightening and forming line. So I'm just going to bring you around the corner here.
So are you bringing in plate stock, or?
We're bringing in coils.
Bringing in coils.
And I'm going to show you how we straighten it.
I'm really interested in that. I've seen lots of stamping lines, but straightening stainless, not nearly as much fun as you'd think.
Yeah, we recycle everything. We had to make a separate scrap yard for the stainless. So this is just a scrap yard for the stainless coming out. We'll go out the door over here. We're about 80% utilization on the painting. Yeah.
80.
So that right there is a really important tidbit of information. Is there anything you wanted to add here, Nick?
No, just I was surprised to see how big of a hopper and system they have there for the scrap metal. It's just, you know, when you see them walking by it and you just start to put scale into proportion rather than seeing it without humans next to it, it's pretty impressive. I mean, it's yeah, 80%, that's pretty wild. You know, I think what a lot of people can relate to is like you know, maybe like countertops in their house, right? Like you get big slabs of granite or marble and you try to use as much of that as possible. And then whatever's left is scraps. And you know, if you go to a countertop store, you know, you can find all the scraps laying around. That's essentially what we're talking about here. Whatever's left over, they're essentially putting it back in that hopper, reusing it, you know, melting it down, reusing it.
That's amazingly high.
Well, they're pretty square panels.
Yeah.
So they're kind of easy to nest.
Yeah, well, I guess so, yeah.
Yeah, it's usually 60, 70, right? But
well, around 45.
Okay,
45,
if you're
50.
bad at what you do, sure. But like we try to, if you're bad, maybe 45, but we try really
no,
hard.
It's on average, that's about, because I look at things in entirety. Now, you're looking at the stainless. I'm looking at,
yeah, if you look at the whole vehicle.
Well, the whole vehicle plus the crap that comes from some supplier or something. Hi, good. How are you? Good meeting.
Yeah, so he's the lead engineer here for our straightening line. This is Dan. He's our head of shopping stamping.
Hi.
So we're just going to walk you through real quick. We'll come over here and we'll look at it. But basically, we get coils in, we feed them in on this side, and out on the other side comes micron precision level blanks.
So this is the first of its kind laser blanking line. What it does is it takes coils, it unwinds them, and it's taking out the internal stresses from the raw material. It's passing them through something called a leveler. All it's really doing is it's got a bunch of work rolls that they're moving up and down, and they're flattening the part. We want to be careful that we don't work the material too much because you do something called work hardening, and then you shear the part later on.
Yeah.
So this was a special development as well. This is something that's primarily used in mills. So
Right.
So did you want to add anything here, Nick?
No, just to remind people, because you're going to hear micron level precision over and over in this video. So a micron, I should have looked this up to clarify, to make sure I'm not wrong here, but is 1/1,000,000th of a meter, right? Just to think of how like small, or maybe inches. I think it's like 1/25,000th of an inch. I think I could be wrong on this, but it's freakishly exact and precise. So just remember that as we go on.
Yeah, and one of the things that I was going to say is that, you know, one of the reasons that he's talking about, they don't want to deform the material too much here is because later on this metal is going to go into a bending process, and the more every time they bend it, whether it's to straighten it out and flatten it after it's coming out of that coil or for anything, because to achieve that micron level of accuracy, that means that these panels need to be perfectly flat, not just like pretty flat with a little bit of warping here or there. They need to be perfectly flat coming into all of these very, very precise operations, so that at the end of the process, you've got that body panel that is not only cut into the correct size and then bent into the precise angles, but then doesn't have any warping, so that you have good body panels that don't have significant panel gaps. And so all of that is huge. And so they have to be very careful, to achieve that perfect flatness, but not to do that by introducing too much bending or stressing the material too much early on in the process, because later operations could actually break the panels if they bend it too much early on. And so they kind of have to save up. It's almost like you have an allowance of the number of times you can do something to the metal before it's going to cause that individual panel to fail, and won't be able to pass quality. And so they're trying to achieve that perfect level of flatness and straightness without using up their allowance of how many times they can interact with the metal.
We actually source it for a blanking line.
So just out of curiosity, why don't you let us know the thickness? I think I know, but I'd rather have you say it. What's the thickness of the material?
So we have two thicknesses. Our doors are 1.8 millimeters thick, and all the other parts, like the sails, the hoods, are 1.4 millimeters thick.
1.4.
Correct.
And we worked hard to get that strength up on the stainless, because the original we were about 2.53, but we actually increased the strength of the HFS over time. So we're able to get, while doing that with the ductility for forming, we're able to still get that strength and bulletproof toughness.
Yeah.
With having a thinner material.
Cool.
Correct. So this is actually designed for 3 millimeter, but it's good that we're not using it.
That's where we started.
Yeah, correct.
So the fact that they are actually using thinner material than they originally designed for means that there's a lot less stress on all these machines that they're using. They're operating well within their design specifications. That means they can run faster, do less maintenance, and then like as they go through, the laser cutters can run faster. If they were going to use that 2.5 to 3 millimeter thickness on the incoming feedstock, then they would actually have to run those lasers slower in order to cut through them. And so they can actually run them faster now with the thinner material. And then of course you have your weight savings by using a thinner material. And so there's just like a whole number of knock-on effects that they get by being able to use thinner stainless steel.
Yeah, it's wild to think that they went from 3 millimeters, which is what presumably they thought they were going to have to be at, to 2.5 and down to 1.8, and still maintain the rigidity, the more or less bulletproofness of it from a door perspective. Like that's like people wonder like what have they been doing the last 4 years? Well, that's
This
a
is one of
pretty
the
big
things.
deal. Yeah, like the metallurgy and the material science that goes behind that is, I mean, that's wild. That's a huge difference. It's 50% reduction in thickness.
And then only 1.4 millimeters thick, for all the other panels besides the doors. And so, yeah, just like very thin metal, and its ability to make the Cybertruck so stiff and, allow a lot of the load to be transferred through the skin. It's not a complete exoskeleton, but those body panels are structural. They are carrying load.
This shows a good overview of the line. So you have the uncoiler, as I explained, where the actual raw material, we call that a coil, is being loaded. It's being unwound as we speak. It's going through the leveler or straightener, depending on what you want to call it. Then it's going into the laser booth, which is what you see right over there. It's airtight, light tight because of emissions and whatnot. And these are two lasers working in tandem. And right now what's being cut is the hood for the Cybertruck. It cuts up to 30 microns, and it's the first laser of its kind to do that. Typically, these machines cut at 1 millimeter. This was a special development with Tesla and Shure.
So just again, you bring in one coil, the coil becomes empty. Do you do a tailored blank from the old, well, what's left of the coil and the new coil? Are you welding?
No,
Or do you?
there's no welding.
No,
We
so
just,
that
when we run out of material and the blanking, then we put a new roll in.
Put a new roll in. So we actually have different coils for different products. So
see.
what we really do and what's beautiful about this line is if you think of a fender, normally on a 2D flatbed, yeah, you can get 2 fenders,
Yeah.
but this gives you tighter nesting. So you can get a fender after a fender after a fender,
Yeah.
and you can optimize the width. So this improves the scrap utilization for the overall.
So does that mean that the coils are tuned to the parts?
Correct.
Okay, and that's why you don't have to weld anything together.
Correct.
Okay, good.
Let's go check out the blanks at the end of the line.
Yeah.
Yeah, that's impressive. So a lot of times when it comes to, the stamping, it's you need a certain amount of width between, each stamping that you're going to do, right? Because you need room for that to happen or for any cutout. But what they're saying is because they're down to 30 microns of precision that they can have those cuts happen closer and closer together to save all of that waste or all of that material. That's wild. And this is clearly a new laser. They said that no one's ever done this. The precision of it. I mean, that's I love that the inventions of not just the product, but the tools to make the products as well.
Yeah, and then it was co-developed with Schuler, so it's cool to see a company. Schuler is a German manufacturing company that they make these precision laser cutting tools, and so because it's more precise, they can get the things closer together. But then also the quality that you couldn't actually achieve consistent panel gaps with those stainless steel body panels if your feed coming into the original thing has an accuracy of 1 millimeter. I'll put up the here's Grok's answer on what a 1 micron is 0.0000393701 inches. So they're doing 30 of those. So yeah, like 0.001 inch tolerances that laser roughly is cutting to. And so, it's really hard to detect 0.001 inches with the naked eye. So that's, because they're starting out with such a fine precision on these blanks, that's going to feed forward into all the later production processes and help them be, high quality. And hopefully, I didn't check Grok's math on that, so hopefully it does know how to convert microns to inches, but even if the numbers aren't exactly right, the overall point is still the same.
Yeah, I googled it. It is 1/25th of a thousandth of an inch. 1/25th, 1/25 thousandth of an inch. Yeah.
Oh, I forgot the other point that I was going to make on that is that, I saw somewhere else that Lars said that they are the only customer that is buying these stainless steel HFS coils. And so they are able to work with their supplier. So that's another way that they're able to get such good utilization, that 80% utilization rate or 20% scrap, is that instead of working with a standard size coil that is a standard width and a standard length, and then trying to fit all of their parts into this standard cookie cutter size coil, they can get the exact width that they need and the exact length that they need so that the coil ends precisely where it needs to end to begin a new thing of parts. And then the width is perfect so that they can use the full width and not have extra at the edges. And so because they are the only customer, they can actually do that with this supplier.
And why are they the only customers?
Just because no one has ever needed this. HFS is a custom alloy.
Yeah.
I'm not sure. This is one of the questions that I have, and I wish I could get an answer to it. I do not think that HFS is the exact same alloy as the 30X cold rolled. I mean, they are both 30X cold rolled stainless steels, but I think that X part is slightly different between what is used in Starship construction and what is being used here in Cybertruck. I would almost bet dollars to donuts that that's going to be the case. And because it's a custom alloy for this manufacturing process, there's no other customer. A, it's going to be something that Tesla has exclusive rights to, and B, there's not going to be anyone else who has all the production tooling and a need for that exact specific alloy.
Yeah, I just think it's so cool that they make their own alloys. I mean, that's just you don't see car companies do. You don't see many companies doing that.
Mm-hmm. Yeah.
This is one of our transfer presses. This is the smaller one, but we just make small
Yeah.
parts there. We actually insource about 70% of our stampings for Model Y and Model Cybertruck. It's quite a
Well,
bit.
when I did the study on why we should use castings,
Yeah.
I did that study cost me a lot of time.
Yeah. So this is just separating the good parts from the bad parts.
Okay.
So because once more, as you saw in the laser, everything's being cut on one sheet. So the good parts, like I said, are being separated. The bad parts actually go right down there. And that's what you see going underneath and then going up into that scrap house.
Scrap.
Correct.
Scrap in there. Yeah.
Correct. And then if you go all the way down,
You can see we're stacking them here. And this is how we transfer them.
so right now
that's
that
the
one's
next
being
one.
used.
Okay.
Correct. This one for sale. This one's right here.
So what am I looking at here?
This
You're,
is
you're
just the
basically
storage.
just carding them, right? Bringing
Yeah.
them together.
Correct. So overhead conveyor belts, parts actually
And
come
then
through.
come see it drops one.
Yeah.
And we just stack them up. Very important. The only thing that really can scratch HFS is HFS.
That's right.
So we got to be careful when we put it down that we're not rubbing it against each other.
Yeah. That's one of the other things that most companies will have the stuff coated. It'll have a plastic film, and you don't.
No, correct.
So this is kind of big stuff all by itself.
Correct.
Yeah, so these are the different blanks, yeah?
Yep. Different
Yeah.
blanks, all within accuracy, tailgate.
The best part is no part, and that even includes, there's a number of factors that go into it. Would be a lot of companies would have some sort of a film or plastic coating on that stainless steel, just to protect that finish all the way through the processes to the very end. And they would remove it, as late in the process as possible. Tesla doesn't want to deal with having that on there in the first place because they don't want it to introduce any variation in production. And so they're just working on making sure that every process works so perfectly that they don't have to worry about the stainless steel finish as it's being made. And, they get a little bit of help from the stainless steel itself because it is so hard that it is difficult to scratch by other things. That means that there's less variation in the laser cutting. Plastic actually produces a lot of toxic gases when it's being laser cut. The steel will also do that, but it reduces the different types of chemicals that they have to capture inside of that laser cutting cell. And it's just going to have a whole knock-on effect. And of course, to put on there in the first place costs money. And so not having that film on there saves money, time, and complexity throughout the manufacturing process.
Yeah, it's funny watching this at normal speed versus 2x. I'm noticing different things. So, like, if you could actually go back to where we just were, so if I recall correctly, this is the hood for the Cybertruck, right? That's what's being cut out here.
I believe
And
so.
as you could tell, like just from the manufacturing, all those rolls that they have there, the how automated the line is so far. They already have conveyor belts, taking things up vertically. But then also look at how many hoods potentially are here stacked up. It's interesting to see just the volume that we're seeing just here already, just through this walkthrough. It's it seems like telltale signs to me.
Yeah. Yep.
Tailgate, fascia, hood, doors. Forgot
Excellent.
about that for a second. And then we have a measurement system. So we're producing hoods. So typically we have a periodic quality check
This
So
part's
we'll
cool.
take the part, put it on here. It's just a nice fancy 2D light scanner. And
Yeah.
what it does is it compares the cat that we're
Right.
cutting to in relation to what we're actually
Yeah.
measuring.
So it's like a giant optical
Yep.
comparator.
So just watch your eyes, everyone.
Yeah, it's gonna turn on.
Yeah.
Takes a picture. Hopefully my arm didn't get in the way.
No, no.
No.
You can even sit on it and it'll be fine.
Yeah.
All the points.
Yeah. So all the points are within spec. That's what this is measuring the auto contour.
So you
And
can
it's
see this
checking.
level of micron precision here. You know, Elon's been pushing us
Yeah.
on. You can see some of these 0, 7 microns, 15 microns, 26, 2, 26. These are pretty intense levels of
Yeah.
precision.
Yeah.
And we got to be careful because we're doing periodic checks to make sure this machine has a good CP or CPK, or repeatability is what we call
Yeah.
it.
CPK.
All right, thanks, man.
Yeah.
I really
Thank you
appreciate
very
it.
much,
Yeah.
Lars.
Thank you so much.
Yeah, well, you fast forward through this, and that's common in any manufacturing of anything, right? Whether it's soda bottles, aerosol cans, whatever it is the random, pulling out random samples every X amount to test, make sure that everything leading up to that point that it's still working as intended to. But I mean, that's just so cool. The fact that they're able to measure it with almost like a laser photograph and to verify the micron precision. And even then you can see it's not actually perfect, right? It's like he's saying, 0.07 microns, 0.15 microns, right? So it's like, but to the eye, it's indistinguishable. But that's how fanatical they are on this precision, which to Hans's point earlier, if you're not perfect from the get-go, it's gonna as you move down the line, it's gonna start to be very apparent. And the idea, I think, is by being at the micron level, if you should deviate, you're only gonna deviate at the micron level, not at the millimeter or the centimeter or the, obviously meter perspective, which would be just very obvious. It is just, I don't know. That's next level.
Yeah, and like you said, that's one of the problems with stamping and doing a bunch of welded pieces together, that having the castings be the thing that this bolts to. Those castings are very, very dimensionally accurate as well. And so the old Model 3 body in white that Sandy Munro just crapped on, the way that they made it really contributed to that stack up of tolerances over time, that they had way too many pieces, and every piece has, even if they were doing 10 micron accuracy on every single piece, but then you're assembling 100 pieces together. Well, now when you get to the end of that 100 pieces, you can't say that you're still at 10 micron accuracy, because every single one of those tolerances, if the worst thing happened on every single one of those, then you could have a part that's coming out that was 100 times 10 microns. So that's 1,000 microns, which, yeah, like that becomes very visible. It can become a problem that can cause those panel gaps, and that was what was happening. And so the combination here of using the castings that are extremely dimensionally accurate, and then using such a small number of overall parts, you're only stacking up 1, 2, 3, 4, maybe 5 components to get your final tolerances, and then you're combining that with super strict tolerances to begin with, and you can produce an excellent final quality part.
Yeah, and I mean, as we go through this, like if you just think, like in anything engineering, period, whether it's computer science, whether it's electronics, manufacturing, heat is always the enemy, no matter what. And so when you're stamping, you're putting heat onto it, that force of it. When you're welding, that heat transfers and it walks, right? Metal is a very good conductor of heat. Even when you cut something, the reason you can cut something on that sharp edge is because that's actually creating heat and it's friction down on that object you're cutting. And so as we go through this, like you'll see, like because they're even cutting at that micron level, it helps prevent any of that heat walk throughout all of this, which is what makes this really so fascinating, is that the minimal amount of welding or actual traditional die presses, which would create a lot of that walking or potentially a potato chipping effect, if you're familiar with that.
Yeah.
Did you open that die for me? All right, Dan, let's go to the die.
Look
Okay,
at all
good.
those parts.
So this is our die storage area, and I asked them to open up because the inner panels are also stainless, but they're formed, right? Because the
Yeah.
best way to get section is to have an inner and outer, right?
Right.
Get a lot more
Yeah.
section. So
And I wish that he told us there so it is stainless steel. I'm doubting that stainless steel is also the HFS alloy. That's probably a different, just off the shelf traditional alloy that they're using to form those inner panels. It's something that's going to be much thinner because obviously when they're working with the HFS, those are the parts that are just those big flat lines, the polygons, the single bends, and the inner parts of the doors or the hood or the tailgate that they're about to be forming, those have all those compound bends and shapes that are complicated that it's not possible to do with the HFS. So even though it is stainless steel, it's not the same stainless steel as the exterior.
I
And it's
think
probably
you're
going to
100%
be,
correct.
yeah, it's probably going to be something that's also much, much thinner, so much, much lighter. And the reason that they want it to be stainless steel is so that they can weld those body panels, the inners of those body panels to the outers, and not have any problems with corrosion at those. Because if you join two different types of metal together, a lot of times, different metals have different reactions, but a lot of times anything that is too dissimilar, if you attach it together, you'll end up creating problems over the long term with corrosion and just other quality issues. So they're using stainless steel for that inner in order to make good solid bonds there that they can be rock solid confident in for the lifetime of the product.
Yeah, and welding dissimilar metals in general is a pain. It tends, to your point, that tends to be a big fail point on many. I mean, I just items in general, things that are welded. Um, you normally try to avoid that as much as possible, but sometimes it's inevitable.
forming stainless as an A surface is kind of hard because you get, drag marks, whatnot.
And when he says a surface, that means it's a surface that could potentially or is definitely going to be seen by the customer. And so the surface finish, you want it to be perfect. You don't want it to be blemished. And so you don't want any scratches or marks or funky appearance in the areas that are going to be seen by the customers.
And so we had to work really hard on this process as well.
This
So-
is our front door inner.
It's
Up one
two out
side.
die. And you can see this coating. It's a
Yeah.
Well, we went through a lot, aluminum bronze coating here in the inserts to make sure that we don't get those drag marks on the stainless itself. And I think we have the world's fastest, first only high-speed A-class surface stainless press.
We're making
It's
10
analog.
strokes per minute over here. That's the
10
press, 10
strokes
strokes
per
per
minute.
minute. That's the press that runs it. We do 8 panels inners, as Lars stated. We do tailgates, hoods, the 4 doors, lamp cans, things of that nature, but
Yeah.
10 strokes per minute. So roughly 600 an hour at 100%. Again, this is the front door inner, like Lars stated, dual. And then this is
The
out.
And so when he's saying 600 per hour, what that's talking about is one of these full, you can see here. So these dies that they're looking at, that is, those are not the actual panels themselves after they have been stamped. These are the shapes of the pieces that are actually going to be pushed into that stainless steel to give it that final shape. But you can see that there's 2 actual door panels in this. And so if this specific one that we're looking at were to run for a full hour and create 600 blanks, that would equate to 1,200 doors. And then some of the other things that they're talking about are going to be smaller, like the lamp cans, for example. It may be 600 tailgates because the tailgate is going to be a very large piece. But then maybe 1,200 rear doors and then 1,200 front doors. And then you may be able to do a whole bunch of lamp cans all out of one overall blank. And so, it may be 2,000 or 3,000 total blanks for the lamp cans that they can make in an hour. And so, yeah, that is, that's an incredible production rate that they'll be able to sustain, once they get all this stuff ramped up.
Lower
Yeah.
half.
Yeah, and he just real quick again. Remember, again, they're talking about a world first to be able to do the race we're talking about. And then I also I'm just now noticing a cool little Easter egg. Look at the shirt, Melt Center. I think that's awesome.
Nice.
In the upper half.
Wow. That's pretty nifty. I've never really stamped stainless steel without a coating.
I don't think anyone has.
So, well,
This is the
there may
first
be,
one.
but not me.
Certainly
We're all
not.
learning.
Certainly not for like an A surface quality part. Like there might be people making it, maybe like stainless steel pots and pans, but then they polish them, right? And they make it.
Yeah, well, yeah, polishing is that's the biggest cost with pots
Yep.
and pans.
Yep.
The stamping and whatnot, deep draw, whatever.
Super easy, right?
No problem. This though is something I've never seen before. I've never used a bronzish. What'd you call
Aluminum
this?
bronze
Aluminum
alloy.
bronze.
It's from.
How do you coat it? Is it?
It's actually the whole material. It's not coated.
This is aluminum bronze,
Yeah, like the whole.
and
whole
you can
difference.
stamp with it.
Yeah, I mean it's hardened. We have a coating on top, but like we found that it was the best material to use.
I just love how like mind blown Sandy is here, and it kind of emphasizes the point that you made, Nick, about like this is world's first stuff. No one is doing this, so this is the machine that builds the machine, and this is where they're focusing so much time and attention and innovation and doing things from a first principle standpoint that make it possible to ramp up production of CyberTruck to high volumes in high quality at low cost. And so the fact that they don't have to do anything to these panels after they stamp them, they're just perfect. They look perfect. They're the exact right size. They're the exact right shape. They're going to fit perfectly with all the other parts that they're going to interact with. And so they spend a whole ton of time innovating on how to do that so that then they can just crank out those perfect parts time after time after time, super easy, super efficiently, super cheap.
Yeah.
I
Yeah.
think
And
specs on.
you also have to, don't be myopic about it just because we're talking or looking at this line, but this is the culture of Tesla. This is what they do. So you can extrapolate this to every other thing that they do. I mean, these are things that we don't even see that they're doing, right? They're innovating in. And so take this from just a Cybertruck manufacturing line and think about what they're going to be doing with the next gen vehicle, with Robotaxi, the things they're doing with the FSD, right? So this is why they can go ahead and send out to these other automakers how to go to a 48-volt system. It's because they're not worried. They're not worried about people catching up or getting ahead of them, because these things here, right? And this extrapolates throughout the whole company. I mean, this is not just it's just this line that happens to have all these innovative things
On it.
Yeah, we're still playing with lubricants.
Yeah.
What kind of oils we're using, how much of. So we're still
Really?
dialing it in.
Because when you use steel, we get drag marks.
Yeah.
Aluminum can't last, right? So we obviously have to replace these inserts a reasonable amount of time, but they're lasting quite a lot longer than we thought they would.
How many hits you get on this thing?
Well, how many
How
have
many
you
do you
stamped so
think you're
far?
going to get?
So far, we probably stamped about 1,000 to 1,200 of each part.
I think we're going to get about, based on our prototype trials, anywhere from 50 to 100 before we start doing rework. But you rework a stamping die nominally, every time you take it out a little bit. Right?
Yeah,
So
we're constantly dialing in quality.
we're not going to throw the die away. Just going to rework it, make sure the finish is there.
Most of our PIS scores
Wow.
now in the upper 80s.
PIST is our points in spec, so we try and get 100% is a perfect spec, like zero nominal, we're upper 80s, 90s.
We're currently in the upper 80s. Started in the low to mid 70s, now in upper 80s. Every run we try to improve.
I just want to take us back for a second here, if I can find it. This screen here where they have all those points, and each of those things has a tolerance on it, the 0.07, the 0.15. So that's their PIS score, which I love that they call it that, points in spec. That's saying for every point that they're measuring, that it is within whatever their tolerance is on those. This is for the later forming die, but you can imagine the same exact process going on where they're measuring, and this is a very simple two-dimensional part that they're looking at, that formed piece is going to be 3 dimensions. And so they're going to have all of the dimensions that are important around the edge, and then all of the depths of those 3-dimensional pushes into the metal, all of that stuff. And so for him to say, you know, right now they're in upper 80s on their PIS score means that just the overall dimensional accuracy of that part is good. And he says, you know, they're getting better, that they started out at 70, I think, and they're on their way, you know, trying to be up into they're almost to 90 already, and they're working to be in the high 90s to 100 range.
Every run we try to improve.
Well, there you go. 2
Let's-
things I would have never guessed. Yeah.
All right, let's go up the stairs here.
I love seeing him just
and we're
shot.
just gonna walk-
Like,
Yeah.
just two things I wouldn't have expected, and we've barely seen anything.
Yeah, we've only been here for 17 minutes so far.
Yeah.
And that included that long commercial for the 3D systems.
walk
Do you
around.
guys want to see hot stamp from ground level
Yeah,
or top level?
Yeah, we can look at hot
Oh,
sand.
yeah,
You know,
yeah.
and then we'll walk.
My
up the
big
stairs.
thing is I want to see how you're forming.
Yeah, we're
the,
gonna go up and go-
pieces.
Show you that. It's much simpler than you think. I think.
So here we have 21 furnaces. There's 3 furnaces, 7 chambers each for a total of 21.
Yeah.
We heat the material to 900 degrees Celsius. Then we put it in a press. It's one station. The upper and the lower dies are held in place for anywhere from 6 to 8 seconds with water running through each. And we're basically in a way quenching the part in a way
Yeah.
with metal.
Yeah.
So that is a super fascinating tidbit there. He's saying that as you know, they heat up the metal part. I think the parts that we're about to look at are going to be the body side inners and body side outers, or the door ring for the CyberTruck. And so as they're forming it, these parts are not necessarily made of stainless steel. They're made of boron steel. And so they heat up this boron steel super, super hot. He said, I think 900 degrees Celsius, which is over 1500 degrees Fahrenheit. And then they put it into a stamping die and they smush it into the shape that they want it. And those dies that they're smushing it with, they're actively running water through there to then absorb the heat from that metal away. And so it is when you are working with hot metal, you really want to control the exact rate that it cools, and not just how fast it cools, but exactly where it cools, because there will be points in the metal that are hotter than others. And so in order to produce a part that has the exact properties that you want it, you really need to control that entire cooling process. And you know, Tesla has proven that they're masters at this. That's a huge thing that goes into how they're able to make these perfect giga castings time in and time out. So is there something you wanted to add there, Nick?
Yeah, I was just gonna say, it's been years since I took a materials class, so I don't remember the word for this. But if you don't cool it in the right and potentially uniform way, you can create these like micro cracks within the metal itself, and down the line, you know, that will actually cause a break, a crack, a damage. You actually used to see this with ships, believe it or not, where ships, the bow of the ship, the front of the ship would fall off. Like this was an actual problem for tankers for many, many years. So it's cooling it is very, very imperative to the whole process.
Yeah, and so they're able to achieve this perfect cooling not by when he talks about quenching, what you would normally do is you would take it out and you would just either spray water or oil onto it,
Yeah.
or you would dip it into a full bath. And you can realize like you don't have nearly as much control doing that as you do by actually flowing water or oil or whatever it is. I think he said it was water through your dies in a very controlled way that you can control the flow rate. And by controlling the flow rate of your water and the exact location that water is flowing through, you can perfectly control exactly how much heat is being extracted, exactly how fast, and exactly where. So that's a really cool process. And I'm sure this is not something that is unique to them. This is going to be something that is relatively industry standard, but as an engineering nerd, it is super fascinating.
Yeah, I would say it's pretty much an engineering standard in anything. I mean, we can use an example with Dojo, right? Dojo also has a cooling liquid that goes through it, and you want to keep the liquid running and flowing. To your point, that way we have the constant temperature that's going in there cooling, so that heat transfer can happen consistently. Because if you just if you dunk it, let's say you just dunk it, all of a sudden that surrounding water is going to be warmer over time as that heat dissipates, right? So a constant flow maintains your cooling temperature until you get it to where you want it.
Yeah, and you don't have to worry about, okay, like this time, I dunked one in and the bath was this temperature, and then the
Yeah.
next one I
The
dumped
next one, yep.
is higher, and then it gets hotter and hotter. And so then you have to figure out how to maintain the temperature of your bath. And they're already doing that with the liquid that they're flowing through that die.
So this is made by AP&T out of Sweden. We have a second one coming just to the west of this one.
So you come in here, probably see the oven, right?
Yeah, you're good. So this here takes it off a D-stacker where it's centered, and it loads it into one of the 21 chambers. Then another one pulls it out and loads it into a centering table. It's centered, then it gets transferred by a last feeder into the die. We can see the die over here if you'd like.
Sure, why not?
So each one of
but
these,
it's not working right now.
No, it is. It's just each one of them's heating up. So each one of those chambers is a different door with a different panel in it heating up. We can go to the forming side. What's that?
How much time does it take for heating up?
We got
Like
21
15?
stations. So total strokes per minute on this is also around 10, 12, right?
This one I can make, it's 23 seconds for inners, 25 seconds for outers. So I can make 144 an hour with the inners and 150 an hour with the outers. At 100% OEE. At 100%.
Yeah.
Here we go. Got one coming. I hear it.
There should be one opening up soon. We may have just come at a bad time.
We might have just come right when they stop. Here we go.
Here you go. You want to see it? Hey, right over
here. Come on.
Wrong way.
Camera's in here. You can see it's pulling out the hot blank right now. You see that red hot blank? It's going to get laid in. It's basically a noodle kind of right now, very, very soft. And like, put it down. We'll form it here with this gripper, and then we'll just drop it into the stamping press while it's still hot and hit it one time. Boom.
Again, it usually holds it for about 7 to 9 seconds.
Yeah.
And we can show you what the parts look like when they come out.
Back end.
Yeah.
Got all these stanchions up.
Yeah.
So, as you can see with all the equipment, we're ready to roll at like high volume. Now it's just like, how do we ramp, go slow, get quality right.
Yeah.
Yeah, there's a view of the press from the side.
Should open up. Yep, now it's opening up. And you'll see that's the fully formed door ring that I was talking about. Are you doing inners or outers right now?
Right now we're doing inners, inner to left.
Thanks.
Here's what they look like when they're done. This is a body side inner.
Check for heat.
It's gonna be a little hot. It might be a little hot.
No, it's not even warm.
Now,
This
just
will
so
cool
you
down
know,
fast.
we're actually going to unload this with a robot. We have what's called an automatic, basically using a robot to automatic racking system.
Yeah.
So they're going to automatically get put in these racks, and we're going to take them off with forklifts. Right now, we're not 100% ready to do that yet.
But then they go up this conveyor, right? Well, not these parts, all the parts. They'll go up here, and we'll go up there, and we'll show you how we form the stainless from there.
So boom, we got our lift right up there. We supply body shop, which is right over there.
Cool.
Any other questions? Or?
No.
Yeah, so I love seeing that, they're planning to do all of this racking automatically. They're not at a production rate yet where that's completely necessary. And so they haven't finished that part. And so we kind of get to see where they're at. One of the things that, Stephanie said is It's cool to see how few employees are here. Part of that is because this is in the evening, and so they have. I think Lars will say this here in a second. They have some employees that stayed around in order to help make all of this tour possible, and so they're kind of facilitating some stuff. They've got some machines running just so that Sandy can see them, but they're a lot of what they're doing here, they're not running full shifts, and this is after most people have gone home. So it's not a completely accurate view of how many people would be working here in the middle of the day. But even that said, you can just see the level of automation that's here and how little is actually going to need to be done by people manually once they get this thing fully ramped up.
Yeah, just a couple quick takeaways. So, one, he gave us some numbers. He said that they have, I think, 24 stations there and that they can do about 144 inners and outers an hour. If you take that, say 20 by 24 hours, take that by 365. Obviously, that's not realistic, right? But if you just assume that, that comes out to about 1.2 million. All right. So obviously, you need inners and outers. So cut that in half, make that about 500,000. Add it into what Lars was saying, that as you can tell, we are ready for scale. Is what he said. So and then with everything we saw, all those cut out pieces, all those hoods stacked up. I guess what I'm just trying to get to is I think that Tesla's been sandbagging us a little bit here.
Yeah, I would certainly agree with that.
Yeah, I mean, not, again, set expectations, but
Yeah, it'll be
there's
a
a lot going
while.
on
I
here.
mean, between getting all these production processes working perfectly and dialed in, but then also getting the entire supply chain for Cybertruck ramped up. They've got to get their whole 48-volt architecture, like all the parts that they're either making internally or buying from suppliers for that. All that stuff has to get ramped up too. But so there's a lot of work. It's going to take time. I don't think we're going to be, making 500,000 of these things in 2024 or 2025.
No,
But they have prepared that their terminal rate eventually, several years down the line from now, they're probably going to be able to make much more than that 250,000 units per year run rate that Elon has referenced.
yeah, exactly. The other thing too is, and again, we don't see this that often, but you're seeing a lot of stuff being done manually by people. You'll see that the what is this? The inner is about to get stacked by two people if that didn't show already. We also saw that they're taking the hood to put it onto the laser camera for testing of the micrometer for level of precision. I see a lot of these things, and it just makes me think of Optimus, right? And how these like just random things that Optimus could be applicable for today. And so it's just as we go through, the factory, it's just interesting to see that and to think of Optimus as well. And like, could we plug this in here? Could we plug it in there? Just based on what we know it can do today.
Yeah, and remember that automate is one of the last steps in Elon's algorithm
Yeah, there's like
for,
five
you got to,
things.
yep, troubleshoot and, remove parts and processes and all that things. And so, having more in the future when Optimus really works, being able to move that step then from, because when he's talking about automating, he's talking about hard automation with dumb
Yeah.
robots. And so if you can add intelligence and the human factor to the robot, you can start automating early on in the process, and using Optimus instead of human labor as you're still figuring out a lot of those things. And that should help you to actually accelerate the overall rate that you can get to. Then eventually you'll still want to introduce these specifically made machines that are going to do a lot of this work, because they'll be able to do it better, higher accuracy, more repeatable, faster, all these things. You're still going to want damping machines and forgings and castings and like all these things. You're not going to do those with hand, or by hand with Optimus eventually. Like, you're still going to use all those same processes, but figuring out exactly how to get from here to there and build the factory that makes all these things, having Optimus in the loop on all of that will accelerate the whole the whole thing.
Yeah, that's funny. Yeah, so you'll start with smart Optimus automation with the goal of ending at dumb heuristic automation.
Exactly.
I've seen a lot of this. So
Probably
all this stuff
never
looks
this big.
about. No, I haven't seen one this size.
Can we go up and over, Dan?
Yes.
Yeah, let's go up and
We
over.
can go up. Thanks, Grant.
So the panels that you saw, the blanks from
Yeah.
the side will come up here along with other parts. And then they'll move in. Right now it's all forklift. You can see all our cherry pickers from construction still here, but they're coming here, and we actually have the body shop on the second floor here.
That's
So it's our-
unusual. Yeah.
Yeah, well, it turns out those are the least number of parts now. We're down to just over
Yeah.
100.
Yeah.
So moving them up isn't that bad, and they're bigger, so we can get bigger, less trips, and they stack nice, so we get a lot of QPC. So we come in here to mainline, but we're going to go straight to doors because we're running low on time. Just to show you doors from forming to final.
No, to finish.
So kind of zigzag. We're only running one shift right now, and nights are doing cleanup and construction and final debug. So it's kind of quiet here, but Werner and the team were kind enough to stay for you.
Oh, that's
So
very,
we can-
very
so we can
kind
get
of
it
you.
running.
Thank you.
Just the layout of the factory is a engineer's dream. So easy to work on things, plenty of room. Don't have to bend over like crazy, weird angles. It's just so much space.
So basically, the doors get built this way and go down straight to GA. The main line goes this way and then gets transferred to our powder coat line that does that black coating
Yeah.
over there. We kind of have a flow.
But you don't use Elpo, right?
What's that?
Elpo, the stuff that everybody else uses. You dip the whole car in it, basically.
No, I mean,
and
well, this is
you don't need to.
it's a soft e-coat with a wet powder just for that black area. So we only have one oven. So we do e-coat it, basically to seal it and cure the sealer. And then we, because the door rings are that boron steel, we need to coat it. So then we put the powder coat on for the aesthetic. We go this way?
Yeah,
We
we go
want to do
this
rear
way.
door.
Yeah. No, we can go
Okay, we'll go
here. I know that this line, bending line, was running dry cycle earlier. I think the other one next to rear door is actually running.
Okay, let's go see the rear one. So we'll talk dry cycle. I'll talk, and then you can show them the rear one. So this is our true bender. It's from Trump. Works special on this. This is the air bender I was telling you about. So this is dry cycling right now. We have one of these for each panel. And how it works is, we'll come in here close. Currently we're running dry cycles, so you can see any faults and whatnot when we're off. So it'll pick up the panels here from that stack that the guys made in blanking. Picks up a panel, and now it's putting it's about to pick up a fake panel. So it picks up that panel, right? We'll show you the one working over there, and it's going to bring it into the true bend, which is from Trump that we worked with. And as you can see, that brake bend comes down, but that's that air bender. It has that V shape with the air flowing on either side to keep it, floating, which when you get the mar marks. Flips it around, it'll do the other side. And then once it's done, takes a good part and puts it back on here, and it'll come out here. So we just wanted to show the dry cycling before we go over and look at the actual part, so you can get the idea of the movements. Now, again, we're in the middle of commissioning all our transfers. Usually we do the systems first. So the good parts will come out here. That KUKA base that's missing a robot.
Right.
We'll pick it up and put it over here, transfer overhead, and go into our door manufacturing cell. So that's it. That's the whole thing that does all the metal forming.
That's a lot simpler than I thought.
Simple is usually better.
Yeah.
Delete.
So
The
we
best
running
part
here?
is no part.
Yeah, this one is
The
running.
best process is no process.
We got front, rear. So this is a rear door.
This is, I believe it's rear door. I mean, this one is able to do both rear and front door.
So this is what you wanted to see. So we get these flat panels in. Now you'll see it actually pull it. Pulls up the flat door blank. we're running about, what speed do you think we're running at about now? Like 25%?
Yeah, I think so.
Here's the air bender. So the top tool forms on the inner. That actually has no air, and the bottom tool is where we're blowing the high-speed air to float it. See, it makes the one bend. That light flash was a measurement. Make sure it's right on.
Yeah.
If it is, it goes back. It's good. Turns around. Does the other bend. There's two on this side, right?
So are you doing any scoring or anything?
Nothing.
On nothing.
Bend radii is 5mm on the inside, right? So it's about 7, 8 on the outside. Anything tighter than that, we started cracking.
Yeah. Well, there's a ratio, and that's the ratio that I would have probably guessed.
Because if you go, we tried to go tighter for fronts.
Yeah, well.
But thickness times, distance. Otherwise, you end up with a knife edge in the middle on the front.
Yeah. Yeah. Well, the deal is that you work.
I think he said that the manufacturer of that bending machine was Trump, which that's not a company that I'm familiar with.
Yeah, me neither. So, let's talk about what we just saw there, because now I'm thinking that I saw something differently than what I thought. So let me tell you what I think I saw. I think I saw that the piece goes in there, and then you have this what were we calling it earlier? The stopper, the joint, the punch. The punch there comes down, but I don't think the punch is actually touching the steel.
So I'm not entirely sure if because at one point he talked about there being air on both sides, and then at another point he talked about there air being only on one side. So if y'all can see my mouse, this piece here, so you've got your metal that's about to be bent, or this may be right after it was bent, I can't tell. But this is your metal work.
It's doing the other side now.
Panel. Yeah. And this is what they're going to bend. So one of the things that's interesting to me is I think they're doing I would really love to know what the angle is that is bent on both of those things. If those angles are not identical and they're achieving two different bend angles with the exact same machine, the exact same punch, and the exact same dies back to back, that's really cool and interesting, because usually you have your dies for a specific angle, and you cannot deform that piece all the way into your die, but to do that and have the precision be 100% accurate would be very difficult. So I'm thinking that both of those bends are the exact same angle, and they would have had to work with Franz in order to design the exterior shape of that to make sure that you could use the same angle in both places in order to achieve that. Or, it could be the other way. Franz could have had two different angles there, and just creative engineering on Tesla's part to be able to use the exact same setup to do two different angle bends, which would be incredible. And so here I'll switch over and we can look at, so this is I started with a standard just cross section. This would be if you cut that machine that we were looking at, in half right here, and you looked at it from the side over here at a 90-degree angle, and you were looking right here. Yeah, if you cut it right here and you looked at it at 90 degrees from over here, and you were looking at this section right here, you would see something that looked roughly like this. And so this, what they have termed the punch, that's the part that is coming down and is pushing into that stainless steel panel. Underneath that, you're going to have the die, and that's the piece that the metal is being pushed into. And this is what I'm very confident that what they're doing, and it may not be that they're only letting this compressed air out at the very bottom. They may be having multiple ports along this die, or it would be coming in from this side and this side. That's when they're talking about an air hockey table, that's what they're talking about, is having little holes in this bottom die where they are actually blowing compressed air out to keep the metal from actually touching, even though they're very, 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 very close to one another. They're not actually touching one another. They may be doing the exact same thing in the punch. That's the
Yeah,
part
that's
that
what
I
I
was
was
having
thinking.
a hard time understanding. It is possible, but the thing about these pieces is that this inner surface is not an A surface, so that's not something that the customer is going to be seeing. And so if it leaves a mark on the stainless steel on this side of the bend, they don't really care. And so I would be surprised if they went through the complexity of trying to add air to the punch. I think it's just going to be in the die, and that when he did mention earlier about um, air on both sides, he was talking about both sides of the V shape of this die, so that they've got air coming in on this wall and also air coming in on this wall. In another video, he also talked about them using bearings, which they may also be doing. And if they were doing bearings, I think my graphic is a little bit off. Those bearings are probably right here at this corner, and that would be where as the metal is being pushed in, it's actually rolling at this fulcrum point right here instead of dragging across a piece of metal. That would also help to prevent. But you've got to realize that if you're flowing compressed air into this to kind of keep an air cushion in between the metal and the die, that it also has to seal in order for that air not to just come out the ends. Um, and so that's also going to be an interesting factor to be able to keep that pressure, so that and it has to be even pressure too along the entire surface of the bend in order for it not to actually come into contact and have a scratch or a problem with the surface finish of those bent metal parts. So
I think you're spot on, especially with the two sides of the air, and that's what ends up floating it. I think you're 100% right.
We started cracking.
Yeah, well, there's a ratio, and that's the ratio that I would have probably guessed.
Because if you go, we tried to go tighter for fronts.
Yeah, well,
But thickness times, distance. Otherwise,
Yeah.
we end up with a knife edge in the middle on the front.
yeah. Well, the deal is that you work hard in it too. If you do anything less than about 4
Four times the
4x,
thickness. Yeah. It comes
you're
out.
gonna get fucked.
Put down the clean part here, and here we.
So that touches on the thing that we talked about earlier with you kind of have a minimum number of interactions that you can have with the metal to bend it and shape it before you start breaking it. And so what they're saying there is if they make that bend radius too sharp and they make that outside angle super like a fine point, then they're exceeding the amount of deformation, stretching, straining that they can do on that metal without it being right on the line of breaking. And this is one of the things that's very difficult. In order to be able to make those sharp bends in the first place, they needed an alloy, and that's why this alloy had to be developed custom and special for the CyberTruck, is because stainless steel doesn't like to be bent, especially in these thicknesses, and especially after it's been cold rolled, where what they're doing when they're cold rolling it is exactly, earlier we saw that they're stamping those body sides and they heat them up first and they stamp them hot. That's because obviously when the metal's hotter, it's easier. You have to use less force in order to create that shape. But the other thing is that, and the reason they have that whole controlled cooling thing, is that when it's hot, it's just like if you're baking something and it starts out as a liquid and then at the end it turns into a solid. there's that transition between the liquid state and the solid state. Well, metal doesn't have, I mean, if you go all the way to molten, there is the liquid state, but when you heat it up, it's not like a binary, there's liquid and there's solid, and these two things, it's either one or the other. There's actually a transition between the structure of the metal in the molten state and then the structure of the metal in the solid state. And if you hold it at a high temperature, this is why heat treats are done, then you can actually change the shape of the way that those metal molecules interact with each other. In changing the shape of the way that crystalline structure works actually changes the properties of the metal. And so, anyways, I say all that to say that when you do it and you work on something that's hot and then you allow it to cool, that when it's done, it doesn't have what's called internal stresses left over that are the springiness in a metal. That is a result of having internal stresses. And when they're doing all these operations on the stainless steel cold, they're actually plastically deforming, which means that they're using force to change the exterior shape and density of the metal. And every time they do that, that energy is actually stored inside. It's like you're compressing a spring, it's stored in the metal. And so when they have done all these cold forming, even so, this bending operation, here's another example. They didn't heat up the stainless steel to bend it. So when they bend it, they have once again stored extra energy in the metal that is a spring type energy. And if they push it too far, then the spring ends up breaking instead of just boiling up and holding that energy. And so most stainless steels would not be able to withstand the operations that they're doing. Most stainless steels would break. So they had to make this HFS, a special alloy, so that they could do all these different things to it and get it to still survive at the end of the day. And not only survive, but then to be bulletproof on top of it, which is, just absolutely ridiculous.
We have the robot.
Oh, very good.
Not quite ready, but
Wow, that base is huge for the size of the robot.
Yeah, we can walk around. It's outside's a
let's
good door.
do that. Yeah.
This might actually be a good time to answer this question from Melody. So they have not discussed anything here about where they are acquiring this metal. I do have another commenter who said that they are purchasing this HFS from Finland. I'm not even going to try to pronounce whatever that manufacturer's name is. I haven't confirmed this. I don't know if that's true, but at least that is the information that I have available to me right now. So, and I'm not sure why they would go to a Finnish company. I would think that there's something special that this company in Finland has in relationship to their ability to make this custom alloy.
I thought it was a local supplier in Texas that was making the steel for it. I thought I remember reading a few articles about it.
I mean, that would definitely be consistent with Tesla's
I could be wrong.
ethos.
I can't
They want to
remember,
try and
but
localize their supply chain as much as possible.
yeah,
Oh, and I'm also
I distinctly
seeing.
remember reading about it.
Okay, well, that would definitely make more sense to me. And like I said, I don't really know one way or the other. So Trump with an F is the name of the company that makes the bending machine. And this would have been another thing where, obviously, in order to do the compressed air part in the die, I'm sure they had to work directly with Trump in order to modify that tool. And so there's not going to be any it may be that Trump is willing to sell these now to other companies if they're interested in it. But this is, once again, a one-of-a-type process, a one-of-a-kind machine, never before used, never before seen in industry. And, there's a whole series of these that they had to do in order to make the CyberTruck and to make it in volume.
Hey, thanks for staying late, guys. Appreciate it. So we get the panel out, and this is ready. You know, as I said, right now we're putting them in the racks. Well, they ran out of racks, but you want to put it in the check fixture?
Yeah, you want to put it in
the check
the
fixture,
check?
just so we can look at it.
Sure, great.
Yeah. So that's it. This is the inner bend. You can see we get a little marring here, but obviously it's B class, right? It's inside the maybe gray zone.
What I was concerned about, or what I was thinking about, was just the outside bruising, not the inside.
Yeah.
I don't care about it.
I mean, you can see on these panels over here. You look on the back side. You can see where you can even see where the air is blown off the dust.
Yeah.
But you come over here, nothing.
Yeah, that's pretty amazing. Actually, you're using two of my favorite, three actually, counting Kuka. They're my
Trump,
go-to.
Kuka, Schuler.
Yeah, if I'm gonna do something, I hate screwing around with junk.
Yeah.
And anytime a purchasing agent or one of those engineers with an MBA says, "Well, I got a good price on it," I have an expression.
There's usually reasons.
Don't save me any money. I can't afford it, and that's the truth. So.
By the way, these are 1.8 millimeters thick.
These are the
Yeah.
full real
And then
bulletproof.
everything else is 1.4 millimeters thick,
Yeah.
other than the domes.
Yeah. Well,
So
you need that extra for the
Well, this
machine gun. Yeah.
Well, the 1.4 is actually pretty bullet resistant too,
Yeah.
but this is actually takes about 75% of the side crash loads just through the panels itself. So, you know, we wanted that extra thickness for the stiffness.
Structural.
So after it goes over conveyance, we'll go into the weld cell.
Yeah, that's you know, that's a big thing right there. In order to, and I love Franz talked about that. You know, they want to put the hardness and the toughness and the structure on the outside as much as possible. So you still have, you know, you've got your door rings. You know, it's not that there's no structure inside the vehicle, but you're trying to put as much of it on the outside as possible. And then when you watch the actual crash test, you can see how the shape of the vehicle after the impact is so much different than a traditional car that we've seen. And that's because a lot of that load is being absorbed by these structural steel exoskeleton panels. So, and I just want to thank you, Nick. I know you've got to head out here. So we're going to go ahead and finish this video. Nick's going to have to drop off, but thank you so much for hanging out and adding your insights to this as we've gone on.
Yeah, it's been a pleasure, Hans. Yeah, this has been absolutely fascinating to watch, especially watching the regular speed time here. I'm sure there's
Yeah.
a lot more that we didn't pick up on that we'll pick up over time. But thank you for having me on. And yeah, we'll have to keep doing these.
Absolutely. All right. See you later.
Cheers, everybody.
And then we'll finish them. And we'll be done.
Okay. Great. So that's one of the things I'm really interested in. How do you affix that to the,
Let's go check it out.
to the rest of the door?
How do we affix it? So we have the inner, you saw from downstairs.
Yeah.
We have the outer. Now we got to put them together.
Right. Without making any marks.
Right, super easy, huh?
Oh, you piece of cake. Yeah.
So we load the inners in here. Is this running now? Is this all? This is all off now, right? Maybe.
What's
Looks like
that?
it. Want to check? Just gonna see if we can turn it on for you. So basically, you know, we don't have any reinforcements on the exterior panels.
Yeah.
We have a couple of hinge reinforcements just
Right.
locally on the inner. So this cell here takes that inner panel and this hinge reinforcement and just welds it together. A couple of spot welds, that's it.
Okay.
Pretty traditional.
Yeah, but
Yeah, Brandon, I love that comment actually, and that is something that I did want to just point out, I think I talked about it in the last video. It's so cool to see how excited Lars and Drew and Franz and Pete and David were in the video that they had last week, just to talk to Sandy, someone who would understand the difficulty of what it was that they had accomplished with the Cybertruck. And even, I mean, it seems like, especially Drew, you could tell that he had watched a lot of the teardown videos that Sandy had done and was excited to share, hey, this thing that you pointed out here in the past, well, we've made some modifications and fixes to that now. And he was proud to show off the quality of the work that they've done. Once again, you can see that here with Lars, that they're just excited for people who will appreciate just the incredible engineering that goes into what they have accomplished. And it's super fun to see.
How do you do it without any marks, any?
Just keep going.
Yeah. Oh,
Yeah, the line is full right now, so we cannot.
Oh, the line's full, so we can't. Okay. So now we bring the outer end. Okay. Outer comes in here, it gets loaded in here, and we have another laser booth. And the laser booth.
Yes, Stephanie. So this is off shift in the evening. I don't think that most of this, and you may be a little bit behind where we're at in the live stream. They talk about the fact that this upper area is not staffed right now, that this is after people have, for the most part, gone home.
Because the exterior surface was the most critical, right? We didn't want to get any burn through, mark through, see
right.
through.
Yeah.
So
You don't want a blue mark either.
So the tolerances have to be basically micron level precision.
Yeah.
In order to get the two together. You have the one part here, Aaron?
Yeah, we got a part here.
Yeah. So this is all closed up laser, but you can see the line's full here, so that's why it's not moving. We can come in here, it's fine. So this is a part as it comes out, and you can see the laser welds coming here. So we actually clamp down on all the corners, and the laser welds go all the way around the perimeter. And what that does, I should really.
I already got it now. I didn't think of that.
So it comes around the perimeter. It actually bends this in just ever so slightly, gives it a little roundness. Helps with the A-surface light coming off the side, so you aren't edge to edge. You got a little tip. But we don't get it. We had to work, I don't know, for months on the current and the heat that's going in, so we don't get burned through with tolerance and whatnot.
Yeah, and so that last part that he just talked about is incredibly critical, because so as they're coming in, they have to weld this inner onto that outer without causing any marking on the exterior surface of the vehicle. And so they have to control, like, this is going to be an incredibly difficult and intricate weld to get right. The great thing is that once they figured it out and they can get it automated, it's super easy to reproduce time after time after time after time. But getting the first ones right is going to be super difficult, because you have to have a weld that gives you perfect, like, you want those two materials to be bonded to each other around the entire exterior surface of those doors. And so they have to be solidly welded together, but you can't use so much heat that you end up creating any warping, or that you usually, when you heat up metal for a welding process, afterwards you can tell exactly where all the heat was. It produces what's called a heat affected zone, which makes visible markings on both sides of the material. And so for them to maintain that perfect exterior finish, and we're only talking about stainless steel that's 1.8 millimeters of total thickness. And so to keep that discoloration from that welding process coming through on the outside edge is an incredible achievement. And just the triumph of engineering once again. Like, this is something else that I guess we'll look and see if Lars talks about it. I would also be surprised, just like they talked about with having the A surfaces for those inner stamped stainless steel parts. I would be surprised if anyone is laser welding A surface parts in stainless steel and not having to do some sort of process afterwards to polish it or improve, like fix the blemishes that were created in the manufacturing process of doing that laser weld.
Trail off. And that's it. It's that simple, and we're done. And now you'll see, like, we do have some burn marks here. What we do is we go into laser ablation, and we just gotta go
Right.
clean it all up.
And that's what I thought maybe you were going to do with the outside of this thing. So I noticed you got two.
Okay, so they actually are doing just a little bit of post-processing, and I'm not sure if he's talking about here on the inner or if he's talking about on the outer, but just to clean up the discoloration that would have been created by some of that process. But it seems like it's whatever it is minimal.
Vibration patches.
Yeah, it's just big oil can, right?
Yeah.
It's just a little damper.
And that's another thing that was going to be a question, but now it isn't. Okay.
So we come out of laser weld. We go into a holding cell because we have a buffer, basically just a buffer.
Yeah.
And then we come over here to finishing. So all these lines are integrated together by Bernard's team and the guys, because, you know, actually every station, you can even see with the robots here, finishing station as KUKA, welding station as Fanuc. They're actually from different companies because we like to like spread it out to people that are good at what they do, right? And so then we come in here to finishing. You want to explain how finishing works a little bit, or?
Yeah, sure. So from welding, we drop it in our handover stand there. Robots will pick it up, drop it in a stand, and we got robots on the other side. They have like a buffing pad.
You see on the bottom of that head that's like inside the shape here, you see those, it's 2 Brillo pads basically.
Yeah.
Hanging down there. Actually 3, right? Three across.
Yeah, I see it.
And all that does is very lightly goes across, back and forth.
Yeah. It does a couple of runs over the complete door. And then they use a different type of pad for the other robot. And then this is a completed part after finishing.
This is what it looks like, done and done. And then that final cell in the closed door, that's where we ablate the
do the laser ablation.
Yeah, so you can see kind of on this one actually, locally these spots, we just go pss, 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 and we get this one's not ablated, that one's ablated. We only ablate the
ones that are exposed.
visible.
Yeah. Cool.
So yeah, he's saying that there is some discoloration that's made by the welding process. They are cleaning it up on the inside of the door only, not the outside, and they're only doing it in the areas where the customer is going to be able to see. So they're not worried about ablating away all of the discoloration if it's not something that is on a visible surface. And then obviously with the Brillo pads he talked about. So that's instead of, you know, at the end of all this thing having to paint these stainless steel doors, the process that they're doing is just basically scrubbing it with, you know, a stainless steel Brillo pad, or whatever. I'm not exactly sure what the material is that they're using for that pad, but that is what gives it that surface finish of looking kind of brushed, just the classic stainless steel appearance. And so, you know, it's much easier to do that, especially with how flat and easily accessible these door panels. You know, there's no compound curves, no recesses here inside of this shape that they're going to have to get into with some sort of thing to brush that surface. And so it should be a very easy to automate process to brush that and create that nice, perfect look on the outside of the door.
These one better.
Yeah, this one is more visible. Yeah.
So you can see the fish bowls, and we do the same thing on the laser weld just to clean it up.
Yeah.
But these are all exposed in the end. There's no paint, there's nothing. That's what we got.
Yeah. Marvelous.
So right now,
so William asked, you know, if we could talk about the aluminum bronze alloy. That aluminum bronze alloy was for the dies that are used to actually make this inner body panel here. And so that's something that the vehicle itself is not made out of an aluminum bronze alloy, but it is something that they probably had to develop. And once again, you know, their materials team, I'm sure, was involved in trying to make the tool that is able to make this shape in a way that can achieve, you know, it's got to be hard enough to bend these parts, and then it needs to be durable so that it can bend lots of them. And that was one of the things that Lars talked about back there was, you know, that I think they can have 50 to 100 strikes before they need to pull that tool out and just do a little bit of work on it to make sure that its shape is exactly what they need it to be in order for that dimensional accuracy to be there. But yeah, they had to develop a special material in order to make the tooling that can create this shape and give it that nice quality surface finish that doesn't leave a bunch of weird drag marks in there that would not look good.
Now these get racked and then brought down to general assembly, but eventually they'll just flow straight down through an elevator. So this whole process runs at a cycle time about 40 seconds when we're at full speed. And we could go faster, but
40
just,
seconds.
Yeah,
Yeah,
40,
well,
80 seconds.
because I was going to say
I mean,
60
it depends
seconds
per
is
line,
normal.
but yeah. I mean, this one is about 60.
Yeah,
50 something.
60 something would be about what I would guess. Yeah.
I
Because you
can
really
see.
don't, because when I went through this factory
Model
the
Y.
first time for the Model Y, that's running at 42 seconds.
Yeah, that's why I
And
meant
then
the
same
model.
thing as the what do you call it?
Berlin.
Berlin factory, 42 seconds.
This one's a little slower, just on volume. You know,
No, you don't need. You
we
don't
need
have to
ad space.
run.
We don't need.
Well, that and the fact that why wear out the equipment?
Yep.
40 seconds. That's working. That's working on machines pretty hard. 60 seconds. They aren't even. I
They're
mean,
really
really,
quick.
they're not breathing hard.
So that's it. Simple and
Cool.
easy.
Well, boys and girls, you've just seen all the best techniques and technologies that Tesla's got to order, or come to order here with the CyberTruck. Now, I'd like to thank all the guys, but especially Lars. But I need to thank the guy that made it all happen. Thank you so much, Rich Otto, the guy behind all of the fun stuff here at Tesla, Rich Otto. Thank you very much. And keep watching because there will be more. Thank you.
Well, of course, we have the teaser. Excited to see what it is that Sandy Munro is going to have to tell us that's more. I can't hardly imagine what more we could want to see. Obviously, love seeing all those machines, love knowing that there is, in the discussion there at the end of the conversation, more room, to improve the cycle time if they decide that that's something that they want to do and need to do, that there's, they're running slower than the 40 seconds or 30 some seconds in Shanghai. And so, all of those things are fascinating. I can't believe that Tesla allowed Sandy to air all of this material. There was a lot of talk about him being under NDA and people thinking, oh, now he's not going to be able to share his insights with us anymore. And yeah, based on his look inside of the Cybertruck factory, I think Stephanie made a point earlier. He may not even need to tear down the Cybertruck in order to know exactly how it's made and how much it costs. I'm sure that he still will do that. That's going to be a huge project. But man, just the amount of access that he was given, I can't thank the Tesla team enough for allowing him not only to see that, but then to share his findings with us. Incredible insights that we got today. And I'm sure there's so many things that were going on there, and especially towards the end, I feel like my mind was a little bit fried. Probably additional insights to be gleaned. I'll have to go back and watch this. But if you saw something that we missed, drop it in the comments. Also, I think that Nicholas's channel, if you happen to be on YouTube, on my channel, it should be in the description. Go give him a follow, subscribe to his channel. His stuff is great. Really appreciate his contribution to this. And for the rest of you, just appreciate you being here with us. If you're coming from Nick's channel or from the X feeds, great to have you here. And I just really enjoyed doing all of this with the community, and have a wonderful, amazing rest of your day.